History of Vector Analysis, Episode 15, Maxwell, Fields, and Quaternions. You are here. Hey, it's old Duck Oler. Welcome back. In the previous couple of episodes, we've discussed the origins of field theory. This was not really a detour because field theory, specifically electric and magnetic fields, were the way in which vectorial techniques were brought into mainstream physics. Many people were involved in this portion of the tale, but none more so than Maxwell. So it's time I properly introduce the man. James Clerk Maxwell was a brilliant Scottish polymath born in Edinburgh in 1831. Today he is considered to be in the very top tier of physicists, along with Newton and Einstein, as well as his contemporary William Thomson. Clerk, or Clark as some say, by the way, was not his middle name. He was born James Clerk. The name Maxwell was appended after he inherited the Middleby estate, which he did in his infancy. The Middleby estate was a significant property of the Maxwell lineage. Okay, it's an aristocrat thing. In addition to being titled, Maxwell was recognized early on as being exceptionally bright. He was sent to the prestigious Edinburgh Academy starting at age 10, where he met and became lifelong friends with Peter Guthrie Tait. After he attended the University of Edinburgh, he then attended the even more prestigious Cambridge. He graduated in 1854 as second wrangler. His friend Tait had graduated as first wrangler 2 years earlier. Between 1856 and 1865, Maxwell wrote, among other things, his 4 great papers on E&M, the ones that predicted the existence of electromagnetic waves that propagated at the speed of light, and perhaps were light, and stated a version of Maxwell's equations, albeit in a different form than the ones we use today. His work was based on the Faraday/Thomson inspired vision of continuous electric and magnetic fields that permeated all of space, with charges as either metaphorical or literal sources and sinks of electric flux, depending upon your metaphysical viewpoint. These papers did not, however, include quaternions or anything in the way of what we would today call vectors. Rather, they used the Cartesian component notation, where the x, y, z terms are treated as separate mathematical objects. In 1873, he wrote his magnum opus, the 2-volume A Treatise on Electricity and Magnetism. This treatise, unlike his papers, included both Cartesian coordinate analysis and quaternion-based mathematics, something that he had been introduced to by his friend Tait. Maxwell never did write Maxwell's equations in their current form with the divergence and the curl operators, del dot and del cross. Nor did he live to see them written in this way. He died at the relatively young age of 48 of cancer. Several years after his death, Heinrich Hertz demonstrated that electromagnetic waves actually existed. On the left are Maxwell's equations as they are written today, and on the right is a page from Maxwell's 1865 paper entitled A Dynamical Theory of the Electromagnetic Field. You can see that the mathematical language of the two is different. This difference is primarily due to the fact that the language on the left simply didn't exist until after Maxwell had died. Instead of writing today's curl of B or del cross B, he instead expressed the same physics in Cartesian coordinate form, with the capital letters F, G, and H expressing the magnitude of the magnetic field along the X, Y, and Z axes. Still, at the heart of his model was the concept that electricity and magnetism were, in fact, fields, continuous in space and similar in many ways to heat, fluid flow, and elasticity. Maxwell was extremely impressed with the fact that Faraday, who was not mathematically trained, could derive the quantified mathematical law of induction. Maxwell credited this to Faraday's ability to visualize or to see in his head the electric and magnetic fields that filled all of space, even in a vacuum. After his major papers were completed in 1865 and before his treatise was published 8 years later, Maxwell spent even more time wandering around the mathematical frontier of classical field theory. It was during this period that he finally allowed his friend Tait to talk him into exploring quaternions with their important del operator due to the way that this kind of mathematics could be used to model the various kinds of fields. Kinds of fields. What does that mean? In 1871, Maxwell published a less famous paper entitled On the Mathematical Classification of Physical Quantities. By physical quantities, he did not mean mass, length, or volume. Rather, he was referring to distributed physical quantities, quantities that today are associated with the concepts of scalars, vectors, and tensors. Specifically, examples of a distributed but nonetheless physical quantity that required only a single parameter to represent them were temperature, density, and electric potential. Physical quantities that require 3 numbers at each point to adequately describe them include velocity, momentum, and the electric field. Physical quantities that require 9 numbers at each point in space to fully describe them include stress, strain, and elasticity. Because of Tate, Maxwell came to appreciate that a single mathematical object, a 4D quaternion, could be used to express a combination of a 1D scalar and a 3D vector simultaneously. This intrigued him. Maxwell argued, quasi-metaphysically, that the relationship between the 3 types of physical fields is as important as the relationship between the different branches of physics, mechanics, thermodynamics, and the new field of electricity and magnetism. The field concept crosses over between these branches of physics. He was taken with the observation that the gradient operator could convert a scalar field into a vector field, and that what would become the divergence operator could do the reverse in a way. The same math held whether you were modeling fluid mechanics, heat flow, or E&M. He wanted a vectorial model of physics of some sort. Perhaps Hamilton's quaternions would do, perhaps they wouldn't. Tate, of course, had read Maxwell's E&M papers with their emphasis on continuous fields. Tate, like the geometer Hamilton, recognized that quaternions were well suited to continuous processes. Tate also explicitly recognized the utility of the del operator to Maxwell's field model. Tate developed the del operator in several ways that he thought could be of practical use to Maxwell and others, and included these in his 1867 elementary treatise on quaternions, which I showed you in an earlier episode. Although, as noted, the text on del was located way in the back. Knowing of Maxwell's newfound interest in what we today call the del operator, Tate wrote to Maxwell on December 13, 1867, "If you read the last 20 or 30 pages of my book, I think you will see that quaternions are worth getting up, for there it is shown that they go through this," and then he writes this sideways triangle symbol, "like greased lightning." Maxwell took Tate up on this. According to the historian Michael J. Crow, the exchange of letters between Tate and Maxwell regarding the del operator continued for some time. Recall that Hamilton defined the product of 2 zero real quaternions as the sum of a scalar and a vector. Okay. He also defined the del operator, written as a sideways triangle, but did not develop it. Tate, after writing the triangle in its present orientation, did. One of the things he came up with, as we saw a couple of episodes back, was this expression, which can also be thought of as the sum of a scalar part and a vector part, or, more clairvoyantly, what would evolve into the divergence part and the curl part. But neither Hamilton nor Tate assigned a specific name to any of these operators. Maxwell took up the challenge. He began with the triangle symbol itself. In their correspondence, Maxwell referred to this symbol somewhat humorously as nabla, a Greek word for the Phoenician harp, which it sort of resembles. The term del for this symbol did not appear until the 1901 text written by Edwin Bidwell Wilson, whom we will meet briefly in a later episode. In an 1870 letter to Tate, Maxwell wrote, "The scalar part I would call the convergence of the vector function, and the vector part I would call the twist of the vector function. However, twist suggests a helical screw. Twirl is free from the screw notion and is sufficiently racy. Perhaps it is too dynamical for mathematicians, so for Cayley's sake, I might say curl after the fashion of a scroll." The referenced Arthur Cayley was an important British mathematician and a chaired professor at Cambridge. And so here you have it, the origin of the terms divergence and curl. Due to the minus sign in the quaternions that would eventually be replaced, the resulting positive flow being in the opposite direction, Maxwell called del dot A the convergence of A. And the term curl, if you had ever wondered, was made in reference to a rolled up parchment scroll. Not quite accurate, since a scroll is actually a spiral, but you get the point. Maxwell continued. I propose to call del squared the concentration of the scalar field quantity to which it is applied. This isn't a bad name. The problem with it is that the quaternion minus sign is there again. In modern vector analysis, del squared equals plus this operator. So with this logic, we should rename it the dilution of the scalar field. But no one does that today. We just call it the Laplacian. If the letter p represents a scalar field, Maxwell wrote, the quantity nabla p is a vector indicating the direction in which p decreases most rapidly and measuring the rate of that decrease. I venture with much diffidence to call this the slope of p, unquote. This name didn't stick. Today we say that the gradient of p points in the direction in which p increases most rapidly, again to deal with that quaternion-based minus sign. So far I have skirted around the edges of the utility of the del operator to E&M theory. Without getting too much into the details here, perhaps my next series will be on this topic alone, let me say a few words about the relationship between the mathematics of del and the physics of electricity and magnetism. Ever since Newton, or Euler or Gauss if you prefer, one of the primary objectives of the craft of science has been to develop quantitative mathematical expressions to represent physical phenomena. As we have seen, Maxwell viewed all of the physical phenomena of E&M in terms of fields. Thus, he sought mathematical tools that could help him express E&M conveniently and concisely in this way. The gradient operator is useful because it can convert or map a scalar field into a vector field. The primary example of this for Maxwell was the mapping of the scalar potential field phi, the green lines, into the vector electric field E, represented by the blue arrows. The physical interpretation of divergence is more comprehensible in fluid mechanics than it is in E&M. In fluid mechanics, Gauss's theorem, actually first proven by Lagrange in 1762, shows that the amount of fluid, and by that I mean incompressible fluid, that flowed through the boundary of an arbitrary but closed surface around some finite source must be equal to the volume of fluid that appears at that source. Obvious physically perhaps, but it allows mathematicians to relate a surface integral to a volume integral, which helps with the modeling process tremendously. You don't need the del operator to prove this. Neither Lagrange nor Gauss had access to it. But when applied by analogy to the electric flux associated with a point charge, del provides a way to relate the surface integral of the mystical flux to a scalar quantity associated with the charge that is inside that surface. That is, what will become the divergence operator is a way to mathematically relate two physical quantities. The first is a quantifiable aspect of the somewhat abstract electric field that has a magnitude and a direction defined everywhere in space. And the second is the highly measurable scalar electric charge, a fairly elegant mathematical expression between the charge and the field it creates. By the way, when I say elegant with regard to this equation, I only mean elegant compared with the Cartesian coordinate approach. Curl is an especially useful mathematical tool. There are few, if any, forces in classical mechanics that are truly circular in nature. For ages, people thought that the planets were swept around in their orbits by circular vortices, but Newton showed that the only force acting on planets was radial, straight line, and that the curved motion was due to the fact that this force was in a different direction than the planet's momentum, which continued on due to Galileo's property of inertia. The mechanics of angular momentum could also be resolved into non-circular forces. But when Hans Christian Ørsted measured the magnetic field around a wire carrying a direct current, he found that the field lines were indeed circular and closed. Okay, how do you mathematically model the relationship between a current flowing in, say, the x direction and the directions of the associated magnetic field lines, which are exclusively in the yz plane? It just so happens that the curl of a circular vector field yields a straight line that is perpendicular to the plane of the circle. Exactly what you need if you can associate the current causing the magnetic field with the curl of that field. Okay? And if you consider, say, the current to be the change of some other quantity with respect to time, say the charge as it flows by, then you have a compact and powerful family of mathematical tools to model your strange new physical phenomenon. Again, you could do this without the curl operator or vectors in general, and in fact Maxwell did in the papers that he wrote up through 1865. But this is much more concise, and as Maxwell would go on to argue in his 1873 treatise and elsewhere, one that provides the user with a visual geometric interpretation of the physical phenomenon, one that Faraday surely would have appreciated. Okay, that's it for this episode. Next time we will explore Maxwell's famous 1873 treatise on electricity and magnetism. We will also discuss his views on the Quaternions that he incorporated in this treatise, both what he thought of as pros and cons. See you then.